Okay, so this is Math 113, Lecture Notes 4, Inverse Trig Functions. This covers the sections 4, 7, 4, 8 in the book. And again, the book is available through my math lab. So we've defined what trig functions are, and we've defined them in 3 different ways: the unit circle, triangles, and graphs. And now we want to define the inverse trig functions. So if we think about y equals sine theta, right? This is asking a question: if you know the angle, what's the sine? And you can think about that in 3 different ways. One is you can say, well, I've got the unit circle. Here's my angle theta. Here's my point x comma y. And sine of theta means I'm looking for this height, right? If I know what theta is. Same thing here. If I know what theta is, then sine of theta is opposite, which is A over adjacent C. And here sine theta is equal to y, right? What's the connection between this? This is hypotenuse 1, right? So sine theta is y over 1, which is opposite over hypotenuse. And if on the graph, if we pick a particular value of theta, say an x value for whatever your theta is, you go up and you find y equals sine of theta. Great. So sine is asking, if you know the angle, can you find the sine? Inverse sine is asking the inverse question. If you know the sine, then what is the angle? So when we're looking at this, this is the sine of an angle. And this is the angle that we're looking for, right? Sine to the minus 1 equals inverse sine. We have to be careful about our notation. When we have that inverse on top of a trig function, it's not 1 over sine x. It's not saying take the reciprocal of sine. It's taking the inverse of sine. Oops, and that's not S-I-G-N, that should be S-I-N-E. It's sometimes called arc sine, so as to avoid the question about what the minus 1 means. So here, if we know the sine, then what is the angle, right? And so if we know the height, right? If this is the height that we know, what's the angle? And we can say, well, that's the angle that has this height. And here it's saying, well, if I know what A and C are, can I find out what theta is? And then finally, if I know a y value, right, can I figure out what the x value is? So if you know the output of the function, do you know what the input was? And the problem is many examples, many angles have the same sine, right? So if we think about a height y in the unit circle, if we're just thinking about the unit circle, there's 2 different angles that have the same sine. This angle and that angle, they both have the same sine. If you think about it in terms of a graph, there are actually infinitely many angles that have the same sine. The relationship between these is that there are also in the circle infinitely many angles that have the same sine as well, because if I go around the unit circle once and then up an angle theta, that gets me an angle that's got an angle theta. And that means if I started here and went through a whole cycle, I'll end up at another angle that has the same sine. So there's lots of angles that have the same sine. We have to pick one. And what we do is we pick the right half of the unit circle. Right, so let me draw a unit circle down here at the bottom. if we want to know what angle has this number y as its sine, we're going to take this angle, but not the one over here. And likewise, if we're going to think about what angles we want from the graph, we want just the angles on this part of the graph, right? So what does that tell us? The graph of y equals sine inverse of x is this. Its domain is -1 to 1. Right? And that's because the output or the range of sine of x is -1 to 1. And so this is saying I want to take outputs of sine and figure out what their angle is. What's the range? So our domain is -1 to 1. What's the range? The range is from up here to down here. And that's going to be from pi to minus pi. And what are the special points? Well, remember from sine, right? We had some special points, 0, pi over 2 had sine of 1, pi, and minus pi over 2 had sine of -1. So if we reverse this, right, because inverse functions just reverse this input and outputs. What angle has sine -1? That's minus pi over 2. Oh, this is from pi over 2 to minus pi over 2. So, right, what angle has sine -1? That's minus pi over 2. What angle has sine 0? That's 0. What angle has sine 1? That's pi over 2. So this point is -1 comma pi over 2. This point is 0, 0. And this point is pi over 2, 1 comma pi over 2. So that's the graph of y equals sine x. So what's the exact value of these numbers? And we have to remember that our basic triangles, 45, 45, 90. Here's my 45 degrees. 1 over root 2, 1 over root 2, 1. So whenever you see 1 over root 2, you got to think 45, 45, 90. The other basic triangle is 30, 60, 90. That's the small angle, so that's the 30. This is the 60, right angle in the corner. Hypotenuse is 1. Short side is 1/2. Long side is root 3 over 2. So whenever you see root 3 over 2, think 30, 60, 90. So sine inverse of 1 over root 2. What angle has, this is asking, what angle between minus pi over 2 and pi over 2 has sine 1 over square root of 2. So you can draw your basic unit circle, say sine of this angle, which we're looking for is 1 over root 2. 2, little small drawing, but that's okay. This triangle has to be a 45, 45, 90 triangle because one of the sides is 1 over root 2. So the angle has to be pi over 4, theta equals pi over 4, or sine inverse of 1 over square root of 2 equals pi over 4. Give myself more space. Sine inverse of square root of 3 over 2 is the same thing. If I have sine is square root of 3 over 2, that means in the unit circle, I've got a height of square root of 3 over 2. But if this is square root of 3 over 2, the angle here must be 60 degrees because we're in the 30, 60, 90 triangle. And 60 degrees is pi over 3. So sine inverse of root 3 over 2 equals pi over 3. What angle has this as a sine? The answer is that. Sine inverse of 12. Not possible, right? You're asking what angle has sine of 12. Sine is always between -1 and 1, so you can never have any angle that has sine of 12. Okay, sine inverse of sine pi over 4. What question is this asking? Well, sine of pi over 4. Sine inverse is asking for an angle. And this is saying what angle has this as its sine, sine of pi over 4 as its sine. So we know pi over 4 is here, 1 over root 2 is this side length. So sine of pi over 4 is 1 over root 2. And we know what that is, it's pi over 4, right? So what angle has the same sine that pi over 4 does? The answer is pi over 4, easy enough. What about this one? This is a little bit trickier because it's saying what angle has the same sine, that's what sine inverse has, of whatever this is, sine 5 pi over 6. Now 5 pi over 6 is over here on the left side of the circle. That's height 1/2. This is all 5 pi over 6. So what angle has this 1/2 as a sine? But sine inverse only plays with numbers between -pi over 2 and pi over 2, angles on the right side of the circle. So the answer to this one is that it's pi over 6. So sine 5 pi over 6 is 1/2. What's the angle between -pi over 2 and pi over 2 that has that same sign? That's 1/2. And then we can draw a triangle to find the exact value of this thing. Here you have to remember that sine equals opposite over hypotenuse. Sine inverse of 4 over 7 is an angle and it's got opposite over hypotenuse equal to 4 over 7, right? So this whole thing, right, this whole thing in here, that's an angle whose sine is 4 over 7. And what's the cosine of that angle? So we draw a triangle. This is my angle theta. This is 4 over 7. So here's an angle whose sine is 4 over 7. We'll call this A. First off, what is A? Well, A squared plus 4 squared equals 7 squared, which is the same thing as A squared equals 49 minus 16, which is 33. And so A equals square root of 33. So cosine, so katoa, cosine is opposite of hypotenuse? No, so katoa, adjacent, sorry about that, over hypotenuse. So it's square root of 33, 7. So once you've got this, you know what the opposite and hypotenuse is, you can find the adjacent, and then you can find the sine. Okay, same thing here, exact value of tangent of sine inverse of 3/5. So sine inverse of 3/5 is an angle well, this equals, I know I put a semicolon there, angle with, remember that sine, SOHCAHTOA is opposite over hypotenuse equal to 3/5. So we can draw a triangle. Opposite is 3, hypotenuse is 5, A is the adjacent, this is an angle. This angle has, sine of that angle is 3/5. So what is A equal to? Well, A squared plus 3 squared equals 5 squared, or A squared plus 9 equals 25. So A squared equals 16, A equals 4. So A equals 4. What's the tangent of this angle? Opposite over adjacent, 3/4. Great. So that's inverse sine and how to do some stuff with it. You can do the same sort of thing for y equals cosine x. This is an angle. Cosine x is b over c. Right? Adjacent over hypotenuse. If we're dealing with a unit circle, if this is x, then cosine x is this horizontal part. Right? And then again, if you pick a particular x value, you can find a y value from the graph. This is y equals cosine x. So 3 different ways to think about cosine. So cosine inverse of x, asking the inverse question again. If you know the cosine, then what is the angle? The problem with inverse cosine is the same with inverse sine. Many angles have the same cosine. So this angle, if I call it theta, and this angle, which is minus theta, they have the same cosine because they have the same x value. Same thing for, say, this angle and this angle. They've got the same x value, so they have the same cosine. So I have to pick either the top of the circle or the bottom of the circle. We usually pick the top of the circle, right? We have to pick one particular angle that each cosine gets, so we take the top of the circle. And so that means we're starting at 0, and we're going to go to pi. That's here. So we take this one cycle of cosine and say, well, if I pick a particular output from cosine, there's infinitely many of them, right? All these intersections with the horizontal line. And we want to pick out one in particular. And so this is the part that we're actually keeping. All right, so this gives us a graph of cosine inverse of x. The domain is -1 to 1 because sine and cosine are, that's my domain is this way, have outputs -1 to 1. The range is 0 to pi. And the special points we want to know is x, y equals cosine inverse of x. So if we take x equal to -1, +1, the angle is 0. When x is pi over 2, cosine is x is 1, our cosine is 0. Sorry about that. When x is 0, our cosine is pi over 2. When x is -1, the angle that gives you a cosine of -1 is minus pi. Great. And then you can do the same sorts of things that you did with our sine as you did with our cosine. And then finally, we look at inverse tangent. If you know the tangent, what's the angle? And you run into the same problem that we had before. There are infinitely many possible answers to that question. Right? This is the graph of y equals tangent of x here. If I pick a particular y value, there's infinitely many possible x values. That means we have to pick out one of these cycles to be our domain. And so we're going to take this one, right, which runs from minus pi over 2 to pi over 2 as its domain, and minus infinity to infinity as its range. And so again, if you think about tangent, right, if I draw a line like that, that angle and this angle have the same tangent, right? And so we don't want to have multiple answers when we ask the question, what angle has its tangent? So we're just going to use the angles that go from here to here for our tangent. So this is the graph of y equals tangent of x. It's this graph here, pretty much laid on its side. Goes to pi over 2 at the top, goes to minus pi over 2 at the bottom. Its domain is actually minus infinity to infinity, right? So the range of tangent is minus infinity to infinity. So the domain of arctangent is minus infinity to infinity. Domain of tangent is minus pi over 2 to pi over 2. So the range of arctangent is minus pi over 2 to pi over 2. So domain is all x, or if we're doing this in interval notation, the range is minus pi over 2 to pi over 2. Note that it doesn't include the endpoint. This is an asymptote. Arctangent will get closer and closer, inverse tangent will get closer and closer, but never actually touch that. Special points, L 0, 0. Horizontal asymptote on right at y equals pi over 2. That's this one. On the left, right, minus pi over 2, you've got a horizontal asymptote on left at y equals minus pi over 2. So what are the exact values of inverse cosine of 1/2 and inverse and tangent inverse of minus root 3, and explain why they're not the same? So these numbers, 1/2 root 3, that tells me I'm dealing with a 30, 60, 90 triangle. Cosine is x, so I can draw my unit circle. I've drawn a 30, 60, 90 triangle with 1/2 here, going down. So I've got an x of 1/2 and a minus square root of 3 over 2 as the opposite. And so this angle is minus 60 degrees, which is minus pi over 3. Okay, so this angle has got cosine equal to 1/2, so it looks like it should be the answer to that. And it's got tangent is minus root 3 over 2 divided by 1 over 2, which is minus root 3. So inverse tangent of minus root 3 is in fact minus pi over 3. But cosine inverse of 1/2 is actually plus pi over 3. Because the domain for arctangent is the right side of the circle. We want angles on the right side of the circle. But the domain for inverse cosine is the top half of the circle. And the angle pi over 3 is the angle in the top half of the circle that has cosine equal to 1/2. So you do have to be a little bit careful about domains. Cosine, you want angles in the top half of the unit circle. Sine and tangent, you want angles on the right half of the unit circle. So, but then we can do these same sorts of arguments. What's a triangle to find tangent of cosine inverse of 2/3? This is an angle with, now what is cosine again? It's adjacent over hypotenuse equals to 2/3. So we draw a triangle. Here's my angle theta. I want adjacent to be 2, hypotenuse to be 3. What's the third side, which is I'm going to call B? Well, 2 squared plus B squared equals 3 squared. So 9 minus 4, B squared equals 5. So B equals square root of 5. What's the tangent of that angle? That's opposite over hypotenuse. No, sorry, opposite over adjacent. And opposite over adjacent is square root of 5 over 2. Great. Use a triangle to find secant, tangent, inverse 11. So we want an angle with, now tangent is opposite over adjacent. We want that equal to 11. And numbers like 11, they're secretly over 1. Right? So we can draw this as a triangle. Here's an angle theta. This is 11, this is 1. What's my hypotenuse? Well, 11 squared plus 1 squared equals c squared. This is 121 plus 1 equals c squared. So c is the square root of 122. So what's the secant of that? I usually remember secant as being 1 over cosine. I've written myself into a box here because I don't have enough space. So we'll come way over here. 1 over cosine is the reciprocal of cosine, but cosine theta in this triangle is adjacent over hypotenuse. So secant theta is the reciprocal of cosine, so it's square root of 122. Right, and we can do the same sort of thing if we have some kind of function in here. This whole thing, what's the triangle that we're looking for? The triangle has an angle whose tangent is 3x plus 1. So the way I've set up that triangle, its tangent is 3x plus 1 over 1, which equals 3x plus 1. So that's an angle. Theta is an angle whose tangent is 3x plus 1. And I want to know the sine. Well, that means that I need to know what c is. But that's just Pythagoras' theorem again. 3x plus 1 squared plus 1 squared equals c squared. Multiply this out, you get 9x squared plus 6x plus 1 plus 1 squared, which is 1, equals c squared. 9x squared plus 6x plus 2, which doesn't factor in any nice way, but we want the square root of that, and that will be c. So c equals this thing. That's my hypotenuse. So what's the sine in this triangle? Sine of theta is adjacent, which is 1, over hypotenuse, which is this c here, 9x squared plus 6x plus 2. Great, so whenever you see an inverse function, the whole thing means you want a triangle whose tangent is this, right? And here we want a triangle whose tangent is 11, and up here we wanted a triangle whose cosine is 2/3. And then that's basically giving you 2 sides of the triangle. You can find this third side, and then you can figure out the rest of it. Finally, a surveyor wants to measure the height of a building. Surveyor puts on the equipment at a certain point and measures the angle from that point to the top of the building and finds an angle of 52 degrees. Oh, I got my angles backwards. This one should be 34, and that one should be 52. So here's my building, right? It's got a height h. Surveyor measures this angle and finds 34 degrees. And then they go 100 feet towards the building, repeat the process, and they find 52 degrees. So they know this distance here is 100. They want to know what's h. How can you find h? Well, We'll call this distance here x. And then we know two things. You know, tan of 52 degrees is h over x. So h over x is opposite over adjacent for 52 degrees. And we know tangent of 34 degrees is h over x plus 100. So h is the opposite and x plus 100 is the adjacent for 34 degrees. And you can put that into your calculator and find out what numbers they actually are. Tangent of 52 degrees is about 1.28. And tangent of 34 degrees is about 0.675. So from this equation, we'll call this equation 1, this equation 2. Equation 1, we've got h equals 1.28x, right? Multiply both sides of this by x. Equation 2, we have h equals 0.675 times x plus 100. Distributing this 0.675 gives me 0.675x plus 67.5. H is equal to h, right? So 1.28x must be equal to that. Subtract the 0.675 from both sides, and you get 0.605x equals 67.5. And then you can divide both sides by 6.605, and you get x equals basically 111.5 feet. Great, and now we can figure out what h is, because h is 1.28 times x. And 1.28 times x is 142.72. And if we're rounding it to the nearest foot, that'd be 143. So about a 14-story building, roughly. One story is about 10 feet. Okay, so that's inverse Trig functions.